Anybody? You can, if you just started and didn't finished, haven't finished, you can finish it right here if you want to get the 1 point. So those are pretty simple ones. So for example, if you consider this gearbox mechanism, you need just to write down the equation in respect of torques and in respect of angular velocities. So it's kinematic relation and force relation, and basically you need to get that it holds. Yeah, you can try.
About,
which one do you want?
the last one about
Hydraulic.
hydraulic connected volumes.
Yeah, sure. You're welcome.
Thank you. First of all, let's just try one. No.
Another one?
Thank you. Try these questions.
You can write it bigger, such as everyone is able to see.
One. This is question about efforts and question connected with flow.
Yeah.
This is not one. We have to obtain something like that for our connected volumes.
Yeah.
First of all, what do we know? That pressure, which is, we have equilibrity in this
Mm-hmm.
volume, so pressure will be similar for left and right one.
Mm-hmm.
So we know that pressure is force divided by square. So let's try it for first one. Force 1 divided by square 1 equals pressure, which is also equals
F2, S2?
2 divided by square 2.
Mm-hmm.
I think this is true. So from here we can find relation between force 2 and force 1 in order to obtain similar form. Force 2 equals s square 2 divided by square 1 and multiplied by force 1. So this is will be, I think, K. Okay.
Mm-hmm.
And also we can make similar equations for rate. I think.
For the
Q.
for the volume rate,
Volume rate,
pressure rate. Yeah.
So we know that rate for both volumes will be also equal. So volume moves from bigger one equals to the volume which appeared
Mm-hmm.
in second. So Q1 equals Q2, and how we can define these volumes? Sorry, rate. Rate is square of piston multiplied by velocity. So velocity is coordinate divided by time. So this will be volume divided by time. So it is rate.
Mm-hmm.
And similar for piston 2, square 2 multiplied by velocity 2.
Mm-hmm.
So from here we can get something like we should find velocity 1 and there go. So velocity 1 will be square 2 divided by square 1 and multiplied by square 2. This is also okay.
you have effort equals k times another effort, but here.
Oh, so sorry. Yes, this is effort and there is force.
No, here,
Effort and here force. Oh.
Flow.
Sorry.
Two flows.
So
Yeah.
this
Now
is
it's
our
correct,
flow, and this is our effort, I think.
So one effort equals to coefficient times another effort, and here flow equals to coefficient times.
Now, so
Yeah, it looks like true. Yeah. Can you tell me your name?
name or surname?
Both.
Both. Okay. Alexander Horyev.
Alexander Horyev.
Thank you.
Maybe someone else and want to show us another example?
May I for the reduction?
Yeah, you can do this.
Since we know that the power is equal, like this.
Yeah.
We can divide 1 and 2 like this. And also we know that this relation equals to Z1 over Z2, whereas that is
As a gear ratio,
yes,
it is gear ratio.
with
It is
gear-
denoted with an I.
okay.
If you can just no, I mean
So let's say that is our coefficient, and the if we consider like work as effort,
So you need to have an expression for m2 and for the omega 1.
and 2.
You can just rewrite those equations, such as you make sure that you are writing something that you need to write. So effort 2 will be m2.
And it will be
Yeah, z2 divided by z1 times m1, right? Yeah, and yeah, and the another one omega 1 instead of f. Yeah, right.
maybe 1 over Z1 over Z2.
Why did you change?
Because
You see,
omega 1
you see that it's supposed to be the same coefficient, so it's supposed to be z2
right,
over z1.
yes, bingo,
Vadim
yes.
and second name
Adinayev.
Adiняев.
Yes.
На А начинается.
Да, Adinayev.
Maybe final example? All right, let us just continue. So I believe that you now is able to feel the intuition. The another component here is gyrator. Gyrator is the something that allows you to transform energy from one domain into another domain. Let us consider, so here also you can see different examples. I will consider with you the third one. While I'm doing this, you can think about another, and also maybe you can try to derive it by yourself. So here actually is not a motor but a generator. So you can see that as an input here torque is applied, and you as the output you take voltage, but let us do opposite way. So as the input we are going to send voltage and current, and as the output we will get torque and angular velocity. All right, so let us use this kind of causality, and if we choose it, F2 is supposed to be equal to the coefficient k times F1. And E1 equals to k F2. Okay. Let us just put it inside. Let's take a look at this. So E2, it is torque, right? So torque equals to some coefficient k times, what should I write here? What is F1? So here on the upper position I'm writing F1, yeah. So on the bottom the current, so I need to put here I, and from here you can see that torque is proportional, linearly proportional to current, and if I put all the characters into the second equation, I will get something like E1 is the voltage equals to k times angular velocity, right? And if you do know something about, for example, DC motor, you know that this k is called mechanical constant, and it's something that you can find in datasheet of all the motors. So it's like the linear characteristics between current and your torque, and it's something that you send, and here the voltage and angular velocity also proportional to each other. You can think of, you have some kind of battery and DC motor, let's assume, and you just attach your DC motor to your battery, and you will have a constant angular velocity that is proportional to your voltage. If you decrease it a little bit, the voltage, your angular velocity will slow down. If you increase the voltage, your angular velocity will also increase. So those equations probably you saw at your electric classes. All right, so the final building block are junctions. So it's something that allows you to connect all these building blocks together. So how can you attach this gyrator to your masses I to your inductors, all this stuff. So you need to use this topology element. So a zero junction is the one where you have the same effort. It's like the same voltage or the same force, and the sum of all velocities or all the current equals to 0. So you can think of here. So you send here a power, and the power E1, E2, E3, and E4 will be the same, but flows F1 will be equal to F2 plus F3 plus F4. It's like the one that we send here equals to the sum of others that goes out of this junction. And it's opposite for the one junction. So here it's like the flow is the same, but the effort is different. So here it's like you send all power here, and E1 will be equals to E2 plus E3 plus E4. Maybe it ring a bell. Do you remember Kirchhoff's law? Actually, it is an example of this 0-1 junction. And here I do have a question for you. Which one is the one junction, and which one is the zero junction? So once again, the zero is when the effort is the same, such it means that voltage is the same, and one is the one where the current is the same. I almost answered my question. So which one? This one? Is it the 0 or 1? It is 0, and this is 1. Is it correct? So here you can see an equation of effort. So it's not the same. So it will be here 1, right? And current is flow. It's not the same. Opposite, right? Here current is not the same, so 0. And here the effort is not the same, so this one. So it is 0, and this is 1. All right. Let us consider the same model that we had before. Just like in the beginning of the previous lecture. So once again, we have this mass spring damper. So there is a spring, there is a damper, spring with the coefficient of stiffness K, and damper with the coefficient of damping B. We have a gravity here. How can I model gravity? Which building block should I use? So we have those building blocks. Which one should I use to model gravity? What do you think? It's active element, right? So gravity is m times g is force, right? So which one should I use? Flow is velocity, but we know force. We need source of force, right? We do know force. It will be source of effort. Then we have mass. To model mass, which one should we use? So it's the mass has kinetic energy, so it will be I. For the spring, it has potential energy, it will be C. And for the damper, we're going to use R. So it will be, so actually it's not the same, yeah. It will be I, C, R elements. And here we need one junction. And one junction, let me show you, is the one when the flows are the same, so the velocity of this body is the same. So it's like we connected all these bodies to the all these systems together, so we consider a velocity of one part of the spring, one part of the damper, and the mass. So they have the same velocity. This one we put one here. So we have a source of effort, and we send all the power to this junction, and power goes to all the elements. So now let us think about causality. So let's start with the source of effort. So since it's source of effort, we send efforts, and this is the sign of efforts. So in this direction goes efforts, in this direction goes flows. So we need to put a causality sign here, as you can see here. The C element, we would like to use integral causality, and for this reason we'll put a sign here, as you can see on the bottom. For the Y, we also would like to use integral causality, and this is why we put a sign here. And for R, it does not matter, it just depends on what do we have. And we have here, we will find it out actually, what do we have. So it's the question, what should we put, what kind of causality, what should we put? So let us start deriving an equation. So here we just look at the our system, and we construct these bone graphs just from inspection. So we see body, we put I here. We see spring, we put here C. We see damping, and we put here damper. So we didn't derive any equations yet. And now we are starting to derive an equation from this graph, such as we can make sure that it's actually makes sense. So we start with our source of effort. So here we do know the effort. So let me denote E as SE, such as we do understand the origin of this effort. And it equals to, what should I write? What is the force here? Minus mg. It's like our axis goes here, J goes in negative direction. All right. Since we use one junction, we know that all the flows are the same. So I will write down like flow of SE equals to the flow of I element equals to the flow of C element and flow of R element. So we know that all of them are the same, and actually, since it's 1D mechanical system, its velocity, so, and we here have x, so it will be x dot. It's our velocity. Now let us consider C element, our spring. So here we use, let me go to the picture. Yeah, here we use an integral causality, and the integral causality is the one where you do know your flow. You know flow, and you calculate effort. The flow equals to the x dot, and we can put it here. So let us derive it. So I will write it like in general form. So effort of C element equals to 1 over compliance, integral of flow dt. 1 over compliance, it will be coefficient of stiffness k. In integral of x dot, so it will be actually kx. Great. By the way, for one junction, we can write down two equations. So let me write it down. So for the junction, for the one junction, we know that all the efforts, the sum of the efforts, is supposed to be equal to 0. But now here we send here input effort, so it will be ESE equals to the sum of all others. So it will be effort of I element plus element of effort of C element plus effort of R element. We know SE. We know now effort of C element. If we can actually calculate effort of R element, so it will be R equals to damping coefficient multiplied with the flow, so it will be B times x dot.
Are you sure about signs effort equation? Because there we have sum of all of them.
Effort, yes, sum of them equals to 0, and here we can rewrite it in the way like ESE plus minus EI minus EC minus ER equals to 0. It's like you can see it in our graph. So we send all the power to this one junction, and then all the power goes to all the bodies. So it's like the power has been distributed among all the components.
So we take signs from
it's like a direction of power flow. So it's like it's going here, and then it's going out. Like it's input, and those are outputs. All right, so we derived this equation, and if we go to the R component, you can see now that it is like the flow in relations, so we need to put a stroke causality here. All right, so we know now effort of source of effort, yeah. We know effort of C element, we know effort of R element, And now we can derive an effort of element at the final stage. So EI will be here ESE minus EC minus ER. And we can put all the components. So EC will be minus mg. EC will be minus kx, and ER it will be minus bx dot. Does it ring a bell? EI, it is the force which is applied to a body, and we do remember the second Newton's law, so it will be actually mx double dot. So we derive the same second order equation. So if we come back to these slide, previously we first of all derived the equation, and then we did the block diagram to create to perform simulation and get plots. But in bond graphs you can start creating this bond out of inspection, and you don't need to really derive the equations. We just did it to make sure that this graph makes sense and all these laws and equations make sense. But you can start using this graph to do simulation. Let me show to you. So there is a simulation package which is called FantaSim, and here you can see the same bone graph that I just derived for you. Yeah, you can go inside all these blocks. Here you can see, for example, here is the source of effort, and here I denote what is the J, what is the mass of a body. Here is the equation of effort and flow. And if we go to the another blocks, you can also see some equations here. So here is the effort equals to the state minus c. So state, it's something that equals to integral of flow. Flow is the velocity, so state, it will be integral of velocity. So it will be what? Integral of velocity. Position, so state here position. And the effort equals to position, so x over c. C is a compliance, so it will be x times coefficient of stiffness. So it's pretty much the same equation that we just derived with you. It is for C element, the same goes for the I element. It's always equation for flow, equation for effort. And I can run it, and here you can see a plot for the x for the position and the plot for the velocity, and it's the same as I showed you in the MATLAB. So it is a graph of just a simple mass spring and damper system, but also I have several examples. What should I? Yeah. For example, the whole robot. For example, here you can see animation of the whole robot with all controllers, with all masses, all this stuff, and it's all based on the bone graphs. So it's pretty complicated stuff here, and you can actually see it that those are I just showed you a 1D bone graphs where all the stuff are just scalars, but there is another version which is called multi-port bone graphs where all the efforts and the flows are vectors and the efforts are covectors. And we will consider about this next lecture about the twist and wrenches. For example, here you can see, where is it? Yeah, you can see just a simple pendulum with two bodies that connected to each other through spherical joints, but all it was modeled from scratch using those bone graphs. As you can see here, this is this is one junction, there is a zero junction, there is a transformer, so all this stuff here. But do not be worried. I do not force you to use this 20 sim. It's only extra if you wish. My point here is that we're going to use MATLAB. And MATLAB actually use all this bone graph stuff. But it's hard to see. But I will try to show you where can you see ears of these bone graphs. Okay, so if we go back to our previous model, so here the simulation model was created out of just simple symbolic blocks like integrator, gain, and so on. But it's not very convenient way if you want to get to model something that little bit complex. Instead of just simulating blocks, it is possible to use Simscape blocks, as you can see here. Also, we can run it. And you will get the same plots for the position and velocity, so it's pretty much the same model. But here, it's just easier to create this system. So here, let us just consider. You have a reference, it's just a fixed point. You have a spring, you have your damper, you have your mass, and those just sensors to measure position, velocities, and so on. So it's like an E element, it's like a R element, it's like a C element. And you can consider mechanical reference as like I element, one element. And the beauty of these Simscape blocks that you can go inside, for example, mass, and you can see your code, source code. And you will, if you consider all the script, the notation is different, but here you also can see equation for the velocities, for the flows, equation for the efforts, for the forces, and you will see it if you consider all the blocks. For example, spring, source code. Here also, V stands for the velocity, that I believe is the derivation of x, and forces is the effort, which is called spring rate. It is coefficient of stiffness times the state, x. So those are pretty much the same equations that we considered. But the Simscape blocks, those you can use it only for 1D problem. And you can recall the blocks that you used for our first practice task, for example, revolute joint, or brick solid joint, not joint, solid block. Let me, yeah. And here you will not be able to see any equations here. So yeah, here you can denote shape, mass, all this stuff. But what is the physics? MATLAB do not tell you what kind of equation they use. And they use the same ball graphs notation, but for the spatial motion. And those spatial motion we will consider next lectures. We will consider spatial kinematics. How can you describe configuration of your robot in Euclidean space using homogeneous transformation metrics? How can you calculate the spatial velocity like twist using these homogeneous transformation metrics? How can you do your differential kinematics like Jacobian? And after that we also consider dynamics and control. So kinematics will be our 5th and 6th lecture, and the 7th and 8th lectures will be about dynamics and control. All right, so this is the idea with those bond graphs. And now we have time to consider another example. So let me finish with this one. By the way, it's an example of something that you need to do as your third practice task. So you will be giving with, let me find it. So where did we stop here? So yeah, I will, with those simple models, so those are 1D problem. I would like to make it simple, such as you can go through all this modeling process, and if it will be clear for you, then it's not a problem to do more complex systems with several bodies. The one that I just showed you, it's pretty much the same, but just rotated on 90 degrees. So you need to consider where is your gravitation and the rotation. So you need to derive an equation of motion, then to do a simulation model using those basic simulating blocks like a game and simulator. Then you need to do another simulation model using Simscape blocks, such as your results will be the same. So let us consider once again the script. So here it's like an example of a report. Here you can see the whole derivation for the model that we considered. Then there is a script to open the simple model with the simulating blocks, and here you can see some graphs for the position and velocity. And then there is a Simscape, not the simulating but Simscape model that use those iconic representation with the springs, damper, all this stuff. And it also make you some plots. And here you can see that actually I put here two graphs, but since they are the same, they coincide. Pretty much the same you need to do, but for those two different models. All right, so I believe that this one is pretty obvious. So just iconic representation of something that you have in your system, and there you can just write down the coefficient that describes the behavior. For example, coefficient of stiffness, coefficient of damping, mass, maybe initial configuration, it is in spring. Yeah. Those two, it's ideal force sense source. So this one is like a source of effort. And if we go to the source code, we can think about it. So the force and the velocity. You can analyze it and you will come up with the same equation as in bone graphs. And I believe that it's everything that I need to say about the third practice task. Do you have any questions? So you can always write in the chat. All right, so let's go back to the presentation. Yeah, we stop from here. And here you can see the bone graph and what it allows us to do. So it's an example of benefits of an example. So let's assume that we want to create a hopping robot that looks like this. The robot that is able to oscillate. From here, when we have just a source of effort, all the stuff that we just considered, we can come up with those plots. What can you see here? First of all, it is position and velocity, so pretty basic stuff. But also you can derive, you can write down the plots for the all energies. For example, here the red one is potential energy, and the green one is kinetic energy. And you can see that first of all you do not have any kinetic energy, but you have potential energy. But while your object is falling, it loses potential energy, but kinetic energy increases because your velocity is not equals to 0 anymore. And the violet line is the Hamiltonian, which is the sum of potential and kinetic energy. And the green, this one, is the damping energy, the energy that being lost into the heat because of the friction and the impact. And this dark one is the sum of all the energies in your system. So it's like Hamiltonian plus the energy that has been transformed into the heat. So now you can see all the energies in your system. And if you want to create a robot that do oscillates and the amplitude is constant, you actually need to create a system that will keep Hamiltonian constant. So you need to calculate how much energy you lost and make energy efficient controller that just compensate all the energy that you lost for your damper. So here you can see another bone graph. It's like the same bone graph, but here there is a two source of effort. It's just the same that we already had, the gravity, and this one is modulated. It's not mean that we have some, it's not constant, there is a function. And this function equals to this stuff. So we can calculate how much energy do we spend on the friction and the damping, and we can send exactly the same force, the energy, exactly the same energy to just compensate all the energy that we lost. And here we can see that the Hamiltonian, the violet, is constant line, is the sum of kinetic energies, and here that the amplitude is constant. And pretty much this stuff we did with the hopping robot, with the Kirill, that we created the energy efficient controller that just computes how much torque need to send into the system, such as we just compensate energy that we lost for the contact. And this is why the robot is energy efficient, that we just give we inject just little energy to compensate everything that has been lost for the friction and impact, to create as possible, to make it energy efficient as possible. All right, so this is your tasks. Let us consider another example. Actually, first of all, I wanted to give you this model, the DC model, as the third example, but I believe it will be just too much. Okay, we'll just consider this as the great example where do you have different components or different domains. So you have electric, you have a mechanical, how they are connected to each other. Okay. So here you can see a picture, a diagram of a DC motor together with the bond graph. But I will just redraw the same bond graph and write down the equations such as I will try to convince you that this bond graph makes sense. Okay, we start with the source of effort, what it will be if our domain is electrical. Is it current? It is source of voltage. And since all our components here are connected in series, not in parallel, but in series, we need to put here 1. If you do recall Kirchhoff's law. So here we do have R element, R that dissipate our energy into heat. We have I element that store energy, and this one will be gyrator. So, R element, then there will be gyrator and I element. Okay, let us start with writing down the equation, for example, for one junction. For one junction, we know that all the flows are the same. So flow of our source of effort, flow of R element, flow of I element, and flow of gyrator 1 is the same. So I will write it down here. Fr, Fi, Fse. But for the efforts, we know that everything that goes in equals to everything that goes out. So here will be effort Se. Everything that goes in equals to everything that goes out. Er plus Ei plus Ejy1. Okay, what do we know from there? We know what is the effort of the S of effort of source of effort, since we just write it down there. So let us assume that for our example it will be 12 volts. So we do know this stuff. Then we can consider R element, and ER will be, if we recall all our equations, it will flow times coefficient of Denver, and here it will be what? 1? Yeah, 1, but what should I write for the effort? So it's C element, R, I element. So here we do know flow. Flow is the current. What will be effort here? What should I write? Yeah, resistance times current, and it's Ohm's law, right? And fourth, so we know this stuff. If we try to write down an equation for the element, and here I will just do this. Okay, I will not do this. I will just comment this. So, if we want to use integral causality, here we know f, but for the integral causality, you need to know e. You do not need effort. Yes, you can use derivative causality, but it's not something that you actually want to do. And now it just tells us that for now we cannot just compute what is the effort goes to the element, because we need to consider what is the load, what is the gyrator, what is the another port. It's like you have a DC motor, but here the current on your inductor will depends on the load, mechanical load. So we need first of all consider gyrator. So you cannot do element as the fourth step, but you need to consider gyrator here. If we go to the gyrator, we know FGY. We know we need to consider effort of this GY1. So I will call this one as EGY1. So I need to calculate what is the E1, and the E1 equals to K times F2. So this effort that we are looking for will be equal to K, some coefficient, times this velocity. What it will be if we consider DC motor? What it will be here? It will be angular velocity and torque. So the effort of the G1 equals to mechanical constant times angular velocity. And now we know all these components, and we can compute EI out of this. So if we put the 5 point, so for the I, it will be that EI equals to ESE minus ER minus EGY1. So it will be something like, let's stick with the U, such as we can get rid of numbers. U minus RI minus KW. And now we did everything physically consistent. If we did a derivative causality, where is it? Yeah. So if we did derivative causality, if derivative causality, EI would equal to coefficient of our inductance times derivative of current. But you can take this derivative in Simulink, but in real life it's not very physically consistent. So it's like a second variant. And if you look at the books, you can find this expression, but this one is not really physically correct. This one is consistent. Okay, so this one is the DC motor, so the conic depolarization bone graphs, and here you can see, I believe it is angular velocity, so if our current is constant, the omega also will be constant. So here I just give you some comments. Here R is the friction, so you can consider shaft, this one, the shaft, and if you want to model viscosity or friction, you need to put here R, and the I element stands for the inertia of your shaft. Then this one is like a link. It's like you want to compute what is the linear velocity, not on the shaft, but on the like the final point of your link. So it's like this one is the DC motor, and this is a link AB, which is attached to the DC motor. Let me show you maybe another examples in 20 sim. So I have a bunch of them. For example, here you can see a picture of a system right there. It's like you have a pipe, you have a bank with water, you have a motor that pump water inside the pipe, and you have a valve here, and your task is just to get the desired height in the tank with the water. So here you can see a simple PID control that modulate how much torque you need to apply to your pump in order to change the level of water inside your pump. And it's not something that actually will be easier to modulate if you do not use bone graphs. But in bone graph, it's just a piece of cake. Here you use a modulated source of flow. So source of flow here will be, since it's hydraulic, it will be volume rate, flow rate. Then you have a transformer, and in the transformer you just say what is the cross section of your pipe. You have a C component here for the tank, such as this all amount of fluids contains energy, and you have R element just to get rid of extra water if you want. We can run it and consider the plots. So here those what it is. It is the velocity of pump, it is a flow rate of the pipe, and the tank height. So our task is to have 1 meter height here, and you can see that it works. It's like an example when you have different physical domains. What should I show you? Yeah, I think we can consider another example with the linkage. For example, here here you can see two plots with the position and velocity for this linkage, which is called Chebyshev lambda mechanism, because it looks like lambda, and it's famous because it can do this fancy trajectory. So the part of the trajectory looks like a straight line. And the same, it's pretty obvious how to do this in MATLAB, right? Because you almost have the same first practice. So just you need to connect joints with the blocks. In 10 minutes you can do this. But you can also do this in FantaSim. It's the animation that I actually did. But this is the bone graph of this mechanism. And if you do recall the level of difficulty, I indicated that if you would like to do this in bone graphs, it will be a nightmare level of difficulty. But it's fun. Okay, but I a little bit joke here, because here you can see this 1D bone graph, and what it, just let me explain you here. It's like a joint, and this in green is a body, and the idea is like this source of flow, it's a source of angular velocity for a link, and those source of flows, it's like a x and y linear velocity for your frame that must be equal to 0, right? Such as the linear component equals to 0, and there is only a rotation motion. And here you do have angular velocity, and if you do know angular velocity, let's assume that you have one link and you know angular velocity. You can calculate what is the linear velocity right here. It will be angular velocity times the r. Since there is x and y components, there will be fx with x equal to vr times cosinus angle, right? And this stands for the y. And this is why it looks so complicated. So the idea here is that it's possible to do this, but it's not correct way of doing this, because it's one deep bone graph here, and it's much easier to model the spatial mechanism, but if we use this proper tool. And proper tool we will consider on the next lectures, when we will consider how can we describe spatial motion. And we'll consider twists and wrenches that will be like flow will be twist, and effort will be wrench, and twist will be a vector of all the velocities. So it's like 3 components of linear velocity, 3 components of angular velocity, and the wrench will be like 3 components of forces and 3 components of torques with the different coefficients here. Such as if you multiply them, you will get power, and if you know this tool, you can model spatial mechanisms using bone graphs. It will be not such complicated stuff. And MATLAB use the same notation there, but it's hidden inside in the script that MATLAB do not show you. All right, so we have like 20 minutes to cover contact modeling. Actually, contact modeling, it's a huge topic. There are courses about contact modeling, but we will cover this topic in 15 minutes. We're going to use the simplest model that exists, and it's just one equation. All right. The idea is that you can assume that now the object is lying on a table, and there is some force which is applied to the table, and here it just equals to mg. But if we consider dynamic contact, this force is a little bit different. And our task is to model how this potential energy transforms into kinetic energy, and then it transforms to the impact. And there is you can do analytical modeling where you have an equation of motion. If you recall this equation, and in order to multiply contact, you need Lagrangian multipliers. But in order to come up with this Lagrangian multipliers, you need to derive all the dynamics, and it's pretty complicated, so we're not going to use it. For this one, you need to have the whole course. But what we're going to use is something which is called penalty-based approach. So the idea is the following. Let's assume that we have a body, and it is a floor. And between the body and the floor, there is some distance which is greater than 0. Then another case, when the d equals to 0, here it's obviously that the force equal to 0, right? But here, force is something like mj. There is no force that there is no component of force that allows you to modulate the impact. So the idea is the following: so that we allow two objects to overlap inside each other. It's like your model penetrates another object on some distance x, and we model force, normal force, equals to be coefficient of stiffness times this penetration plus coefficient of damping multiply with the x dot. So it's an equation of spring and damper system that we're going to use here. So here you can see an example that we have a body M, we have a friction between a body and floor, we have a spring, and in the moment when our body interact with the wall, we have three components. First of all, it's a force of interaction. We have friction here, and we have force because of the spring. So here you can see pretty much the same idea, that let's assume that we know this component, ma, we divide by mass, we get acceleration, we integrate it, once again we get velocity, we integrate it once again to get position. Then we can multiply position with the stiffness coefficient to get force which is generated in the spring. here B stands not for damping but for the friction, so it can be can have a different relationship. So here is something simple, linear relationship, but it can be different. By the way, here I do use not this notation but a little bit different. So the idea is that for the friction we can use a model which is called Coulomb model of friction. I will write this plot once again. So the idea is that there is a relation between the force of friction and velocity. So here is an object that I'm trying to push. The force that I'm applying in the very first moment of time is greater than I need to apply it when the object is already moves. So here I need to apply a breakaway force to force the object to move. But then the force will be a little bit smaller. But if we consider viscosity between our table and an object, the force will be increasing if velocity increases. So, and the same goes here. And this is the Coulomb model friction, and you can find everything about it in the documentation. So let us consider the documentation. Yeah, so I will write here friction. For example, translation friction. It's the Simscape block that models friction, and you can see exactly the same graph that I just wrote. And if you know all the coefficient of friction between the object that you would like to model, you can use this nice equation, not very nice, to calculate what is the force of friction. But basically this equation just describes this curve. And in the model that I just showed you, it's like we know in advance the relationship between the force and velocity, and if we calculate velocity, we can find out what will be the force of friction. And this is exactly what's happening in here. Here I use a lookup table to find out what will be friction force if I know the velocity. So it goes there. So we do know two components. The last thing with the contact, it is right here. So it's like a submodel. So let us consider the lower part. It's like we have our current position. If we multiply the lower bound, it's like the position where is our wall, we can calculate the penetration. So the idea is that if x greater than 0, then the force of interaction equals to 0. So if it holds, then this is the something that goes here, go there. But if it's the position lower than 0, this case, if the penetration is, there is a penetration, if the position is negative, You can take this penetration, multiply with the coefficient of contact, contact stiffness. You can take a time derivative here, x dot, multiply with the contact of damping, contact damping, to calculate the force according to the equation, and you get the force that need to be applied there. And this is how you can model contact. So then here our body just hits the wall, and then it's go to the rest position. We're not going to use this symbolic representation just for idea. In the Simscape there is library, contact library block that I will show you. I believe I will show you how it works in some practice video, because we run over time. But basically it works like you have some geometry. Let me create some drawing. We have, for example, a brick and a plane, and you want to model how this brick is falling down on the plane. You need to attach like a virtual spheres or maybe something else to the points of interest, and you're looking for the penetration of this virtual spheres with your plane, such as it do penetrate, but your object, your real object, does not. So you need to adjust the geometry of these virtual objects. You need to adjust coefficient of stiffness, such as it makes sense, such as your force. You can, you know, if it let's assume that your mass equals to 1 kilogram. It means that in the rest position, force time in the it's like a plot for the reaction force. It will be 0. Then when it in rest position, it will be just mj. But if you put here something with, for example, 1 billion, I don't know, you can write here whatever you like. And if you multiply it with the penetration, you get some nonsense like, and it's go to infinity, but it's obviously not something you will get in real life, right? So you need to put here a coefficient that makes sense. It's not going to give you exactly what are the reaction forces they are. It pretty close when the velocity is close to 0. And in this case, it will be pretty much the same as if you will do analytically with all the dynamic equations and Lagrangian multipliers. But it's not something we're going to do. It's one way. How can you do this? Once again, I will explain you in details in the practice task. But also there is another block which is called spatial contact, I believe, and you can find it only in newest version of MATLAB, I believe in 2020, yeah, and higher. Spatial contact. Yeah, this block is for the Simscape multibody, and what it does, it creates a low polygon mesh around your object, such as you do not need to add any virtual points here, and it works fine. It's just very easy to use, such as you just need to put some coefficient here for stiffness and damping, and that's it. But you can get some nasty experience. For example, if you have an object with a complex shape, something like this, for example. I just do some random picture of spatial weird object. But if you're going to use this block will create just low polygon mesh around it. And if you want to, for example, your robot to interact with such weird object, is going to apply force here, such as it interact with the hidden wall or something. Okay. What else? I believe that's it. Yeah, so here you can see a picture of this block, sphere to plane block from contact library block. So you have like a ball that has 6 degrees of freedom. In respect to your world frame, you have a plane, and you describe interaction between the plane and a ball using this block with the contact modeling. It is the position. The same you can do in bone graphs, but the idea is the same, but just notation is different. I do not want to spend more time here. Yeah, that's it for today. Yeah, we did it in time. So now we have 2 practice lessons, and I encourage you to defend your project, or try to defend. If you didn't finish it, you can ask for help, because I'm going to add more practice that not in the schedule right now, but it will be just a few of them. So you need to be effective, to use time effectively. So I encourage you to defend something that you already done it today, even it's not your practice right now, or at least ask for help, such as I can give you a little bit acceleration, right? Thank you, that's it.